Welcome to the class. Up till now, we have learned various classes of functions like polynomial function, rational function, trigonometric function, etc. Now we will learn about a new class of functions called exponential and logarithmic function. Consider a function f(n)x is equal to x raised to the power n when x is greater than 0, where n is a natural number like n is equal to 1, 2, 3, etc. At n is equal to 1, 2, 3, the value of the function will be x, x square, x cube. When n is 4, it will be x to the power 4, and so on. Now let us plot these functions, that is y equal to x, y equal to x square, y equal to x cube, y equal to x to the power 4. Let us first plot y is equal to x, or when n is equal to 1. This will be the graph of the function. Now when n is equal to 2, the graph will be like this. When n is equal to 3, the graph will be like this. When n is equal to 4, the graph will be like this. Now let us zoom in a little. We can easily see that all the graph, that is x, x square, x cube, x4, etc., all are passing through x is equal to 1 and y is equal to 1. Means when x is equal to 1, the value of all these functions are equal to 1. But as soon as the value of x passes through x equal to 1, the graph of the function which has more larger degree or greater degree moves faster than the graph which has lesser degree. For example, this is the graph for x to the power 4. It is more steep than this x cubed, and this is more steeper than x square, and x square is steeper than x. Now it is clear from the graph that higher the degree of the polynomial function, greater its growth. When x equal to 1, the value of all the polynomial function is equal to 1, and beyond 1, if the polynomial has higher degree, it has higher growth or greater growth. Now a natural question arises, is there a function which grows faster than any polynomial function of any degree? The answer is yes. For example, consider y equal to 10 raised to the power x. This. When x equal to 1, the value of 10 raised to the power x is 10. Way higher than these value. At x equal to 1, the value of all these functions x to the power n is always equal to 1. But for this, when x equal to 1, the value is 10. And beyond that, we can easily see that the purple graph, that is the graph of x to the power 10, is steeper than any of these graphs. That is for y equal to x, or y equal to x square, or y equal to x cube, or y equal to x to the power 4. The purple graph is steeper than all the three graphs here. Now let's compare the value of f100 x, that is x raised to the power 100, and 10 raised to the power x when x is equal to 10 cubed. So let us first find the value of x to the power 100. The value of x is 10 cubed raised to the power 100 is equal to 10 raised to the power 300 raised to the power m whole power n is equal to a raised to the power m into n. This is the value of f100 x. Now let us find the value of 10 raised power x when x is equal to 10 cubed. The value will be 10 raised power 10 cubed is equal to 10 raised power 10 cubed is 1000. So obviously 10 raised power 1000 is greater than 10 raised power 300. Clearly, here 10 raised power x is greater than x raised power 100 for x is equal to 10 cubed. It may be easily shown that for all x greater than 10 raised power 3, 10 raised power x is greater than x raised to the power 100. Similarly, by choosing large value of x, we can easily verify that fx, that is equal to 10 raised power x, grows faster than fnx, which is of the form x to the power n. Fx grows faster than fnx for any positive integer n. By choosing large value of x, we can easily verify it. Now we will define exponential function. Exponential function. The exponential function with positive base b is greater than 1 is the function y is equal to fx is equal to b raised to the power x. We have just seen the graph of y is equal to 10 raised to the power x. Now let us see the graph of 2 raised to the power x, 3 raised to the power x, etc. and discuss some properties of exponential functions. This is the graph of 10 raised to the power x. This is the graph of 2 raised to the power x. And this is the graph of 3 raised to the power x. From these graphs, it is clear that domain of the exponential function is R. That is the set of real numbers. Means the value of x start from negative infinity to positive infinity. And from the graph, it is clear that the graphs of 2 raised to the power x, 3 raised to the power x, or 10 raised to the power x, all three graphs or all these graphs, all such graphs lie completely above the x-axis. It means that the range of the exponential function is the set of all positive real number. One more thing, all these graphs pass through 0, 1, this point 0, 1. It means that 0, 1 point always lies on the graph of b raised to the power x, where b is greater than 1 and x is any real number. And one more thing, see the graphs of any 10 raised to the power x or 2 raised to the power x or 3 raised to the power x. We can see that all these functions are strictly increasing in whole of their domain. So it means that exponential functions are always increasing. And one more thing, for large value of negative numbers like this, as we move from 0 to the left, the graph of the function moves closer to the x-axis. It means that it is asymptotic to the x-axis. Now let's revise the properties of exponential functions. First, its domain is R. Second, its range is R plus, that is all positive real numbers. Third, the point 0, 1 always lies on b raised to the power x, that is b raised to the power 0 is equal to 1 when b is greater than 0, when b is greater than 1. Fifth, for very large negative values of x, the graph approaches to x-axis but never meets it. It means that the graph is asymptotic to the x-axis. Now the exponential function with the base 10 is called the common exponential function. 10 raised to the power x is called common exponential function, and e raised to the power x is called natural exponential function. It is called natural exponential function. What is E? E is Euler's constant. In class 11th, we have learnt about E. E is 1 plus 1 upon factorial 1 plus 1 upon factorial 2 plus 1 upon factorial 3 up to infinity. Now consider the inverse of exponential function. The graph which you are seeing is a graph of 10 raised power x. Now let us plot the graph of y is equal to x. In chapter number 1, we have learned that inverse of a function is the mirror image of the graph of the function on y is equal to x. So this is the inverse of 10 raised power x, the graph which you are seeing in green color. You can easily see that the gray color graph and the green color graph are just mirror image of each other about the line y is equal to x. Similarly, for natural exponential function e raised power x, the graph which you are seeing in red color is the graph of e raised power x, that is natural exponential function. And the graph which is in purple color is the graph of its inverse. You can easily visualize that if you visualize or imagine the black line as a mirror, the red graph and the purple graph are mirror image of each other about the black line. From the graph, it is clear that the inverse of exponential function exists. And the inverse of exponential function is called logarithmic function. So let us define it. Definition 4. Let b greater than 1 be a real number. Then we say that logarithm of a to the base b is x if b raised power x is a. And it can be written as log of a to the base b is equal to x. For example, say we have a number 16. We can write it as 2 raised power 4 or 4 raised power 2. So in first case, we can write it as log of 16 to the base 2 is equal to 4 or log of 16 to the base 4 is equal to 2. Now let us define logarithmic function in terms of domain and range. Log of b from r plus to r, that is from x to log of x to the base b equal to y if b raised to power y is equal to x. From the graph, it is clear that the graph never crosses the y-axis. It means that it can take the value of x from 0 to infinity. It means that its domain is r plus, and the value of y or value of the function can be any from negative infinity to positive infinity. Now, so properties of logarithmic function. Property number 1, logarithm is not defined for negative numbers, that is its domain is r positive. Number 2, the range of log function is r. It means that the value of the log function can take any real value from negative infinity to positive infinity. Number 3, most important, the point 1, 0 always lies on the graph. See the graph? The point 1, 0 always lies on the graph. It means that log 1 to the base b is equal to 0 no matter what is the value of b greater than 1. Now we'll discuss some more properties of log functions. Now we will prove two properties of logarithmic function. Let us suppose log of p to the base a is equal to alpha. Log of p to the base b is equal to beta. And log of a to the base b is equal to gamma. These imply a to the power alpha is equal to p. This is nothing but the definition of the log function. Similarly, b to the power beta is again equal to p. And the last one, b raised to the power gamma is equal to a. Now substituting the value of a from third one to the first, this value here will get b to the power gamma whole power alpha is equal to p. That is b raised to the power gamma alpha is equal to p. Applying the definition of the log, we'll get log of p to the base b is equal to alpha gamma or gamma alpha, whatever way you like. Now log of p to the base b, log of p to the base b is beta. So beta is equal to alpha gamma. That is alpha is equal to beta over gamma. Substituting the value of alpha, beta and gamma, alpha is log of p to the base a, beta is log of p to the base b, and gamma is log of a to the base b. So now we have got an important property. This property is also called base change property. Log of p to the base a is equal to log of p to the base b divided by log of a to the base b. That is, these two bases get cancelled and this a comes under the base, this a. Log of p to the base a. Now let us assume x is equal to a to the power b, that is log of x to the base a is equal to b, and y is equal to a to the power c, that is log of y to the base a is equal to c. Now let us find the product of x and y. X into y will be equal to a raised power b into a raised power c. As we know that when bases are equal, while multiplying, the powers will get added. So the product will be a raised power b plus c. Again here applying the properties of logarithm of x into y to the base a is equal to b plus c. Now what is the value of b? B is this log of x to the base a, and the value of c is log of y to the base a, log of y to the base a. So now we have got an interesting property. Log of xy is equal to log x plus log y. Now consider a case when y is also equal to x. So the above property will be log of x into x to the base a is equal to log of x to the base a plus log of x to the base a. On the right hand side it will become 2 times log of x to the base a, and on the left hand side it will become log of x square to the base a. We can generalize it. Log of x to the power n to the base a is equal to n log x to the base a. One more property. Similarly, x divided by y. What is the value of x? X is a raised power b, a raised power b, and y is a raised power c. So x divided by y will be equal to a raised power b minus c. Applying the definition of the log of x divided by y to the base a is equal to b minus c. B is log of x to the base a and c is log of x to the base a. Log of x divided by y to the base a. So one more interesting property. Finally, we'll write theorem number 5 of textbook. It is nothing but the derivative of exponential and logarithmic function. First part, d over dx of e raised power x is equal to same e raised power x. Second, d over dx of log x to the base e is equal to 1 by x. So this much only in this video. In our next video, we'll learn about use of log function in differentiation. Until then, keep studying. Thank you.